This is Math 261, Section 13.3 on partial derivatives. And the situation here is we have a function z of two variables, f of x comma y, such as this. Z equals x squared plus y squared times x squared. And there's going to be two different partial derivatives of such a function of two variables. First off, we can take the derivative with respect to x, we say. What that phrase with respect to x means is that x is going to be regarded as the variable, but y is going to be regarded as a constant in the process of differentiating. So what this means is to regard the variable y as if it were a constant in the differentiation. So, just how exactly is that going to work in the case of this example? Z equals x squared plus y squared times x squared. So here's how. The partial derivative of z with respect to x is what? So again, what that phrase with respect to x means is to take the derivative of z, looking at x as the variable, and y is going to play the role of a constant. So how that's going to look for this particular z is going to be like this. The first term is x squared. So when we take the derivative with respect to x of that, that's kind of the normal thing, 2x. Plus, now in the next terms, we're going to be careful. It's not particularly difficult, this term, but it's unusual and takes a little getting used to. So we have to regard the variable y as if it were a constant. So if we didn't have y squared, x squared, like if we had 5x squared, we would know what to do to take the derivative without too much trouble. 5 is a constant. Now, that's exactly how we have to treat y squared. So in our heads, we say, okay, that says y squared, but I have to think of it as a number when I do the derivative. And so what we would do here is y squared comes down, and then we take the derivative, 2x to the first, as usual. So the partial derivative with respect to x would be 2x plus 2y squared times x. Okay, now we have a function of two variables, and that means we're going to have two partial derivatives. One is with respect to x. That's what we just did here, where x is the variable, and y is regarded as a constant. We can interchange those roles. And when we do so, that's what we call the derivative with respect to y. That means the variable x is regarded as if it were a constant. So let's see. Z equals x squared plus y squared times x squared. Now we want to take the partial derivative of z with respect to y. So y will be the variable, and x regarded as if it were a constant. Okay, so our first term here is x squared, but x is a constant, so the derivative of a constant is 0. So when we take the partial derivative of z with respect to y, the first term in the partial derivative would be 0 plus. Now y is a variable and x is a constant, so x squared is a constant, a number. Think of it as a number in the process of taking the derivative. So a number we would just bring down, and we take the derivative of y squared as kind of usual. The number x squared we would just bring down, and we do so here. So the partial derivative of this function z with respect to y would be 2y x squared. So that's the idea of partial derivatives. A function of two variables, you have two different partial derivatives that are where you regard one of the variables as constant and take the derivative with respect to the other variable. There are a few different ways that partial derivatives are written in terms of the notation, and here they are. So the derivative with respect to x can be written this way: the partial derivative of f of xy with respect to x. You see the variable you're differentiating with respect to is built into the notation down here. And this symbol, the partial derivative symbol, is used to distinguish it from d dx, the regular derivative. This middle notation is quite handy sometimes. It says f sub x, this is subscript of x comma y. So that doesn't really have an analogous thing in regular Calc 1 type derivatives, to use a subscript to indicate differentiation. But it's a good notation for functions of multiple variables, because you're going to do a derivative with respect to one variable or the other. So to say you're going to do a derivative, you write the name of the function with a subscript, and that subscript is the variable, be it x, as it is here, or y, that you're differentiating with respect to. This is kind of the z sub x notation is less common than the other ones here. And the last one is analogous to the first one, where you have z notation instead of f of x notation in the last one, the partial derivative of z with respect to x. I would say, moving forward, the most common and useful that come up are this, and probably this. This two, somewhat probably a little less. This one, not so much. Okay, and then everything is the same in terms of writing the partial derivative with respect to y, except of course the role of x is now played by y. So the partial derivative with respect to y of the two variable function, the partial derivative with respect to y in the subscript notation, zy, and partial derivative of z with respect to y. Here's a couple of examples. So just kind of talk through these more examples of showing the notation and also doing the process. So to find for this function 3x minus x squared y plus 2x to the third y, the partial derivative with respect to x. So the variable that's subscripted here tells you the variable. The other one is constant in the derivative. So we'd look at x as the variable here. We'd come along, the first term's 3x. Derivative of that is 3. The second term is minus x squared y squared. We had that type of term, that very term actually in our example before. So we want to take the derivative with respect to x here. It means y is a constant, so y squared is a constant. That's why you see y squared coming down. And the derivative of x squared is 2x. Plus, in the function here, the third term is 2x to the third y. Now we're differentiating that with respect to x. So y is a constant, so he comes down like it's a number. So we bring it down. We take the derivative of 2x to the third, which is 6x to the second. So that's where that comes from. Now, for the same function, 3x minus x squared y squared plus 2x to the third y, here comes the partial derivative with respect to y. So we come to the first term, we're taking the derivative with respect to y. The first term is 3x. X is a constant in this differentiation, so 3x is a constant. So the derivative is 0. The derivative of 3x is 0. So we go to the second term. Now we're differentiating with respect to y. So y is the variable. So x is a constant. So you can see the x squared has come down. The negative is out there in front because of the minus sign in the function. And the y is there because we take the derivative of y squared. bring down the 2, and reduce the power to 1. The third term in the original function is 2x to the third y. And we're differentiating with respect to y now. So 2x to the third y, differentiated with respect to y, is, well, think about it like, I'm just going to make up a random number here, 12y. 12 is just a random number, not directly relevant to this problem, but just to show the process. So if this is a number, you're taking the derivative of 12y, the derivative is 12. Well, 2x to the third now is regarded as a number. So the derivative is 2x to the third. Okay. Okay, so this diagram and the next one show the geometry of partial derivatives and what they mean, which is still slope, like a regular derivative in the old days, but we're now in 3 dimensions, so it's a little bit more than just, the 2D XY plane situation. So what's going on with partial derivatives, though, is kind of neat, and here it is illustrating the partial derivative with respect to x. So the reddish-orange colored curved surface there is going to represent the graph of some function z equals f of xy. So for every pair of numbers x, y, if f of xy is some formula, you plug in x and y, you get a z value, and they are what's plotted to create that surface, this kind of orangish, reddish colored surface. Now, we also are given, or thinking about a fixed point here, a point we are given, x0, y0, comma, z0 are specific numbers. And then we go to that point on the graph, on the curved red surface, the x0, y0 point, and we fix the plane. Y, the variable y, equals the number y0. So all the points in 3D here with y coordinate equal to y0 make up that plane. So that's what we're talking about here with the partial derivative with respect to x. Remember, when we do the algebra process, we regard y as a constant, and that's related to this right here because that plane is the plane where the y value is constant, y equals y0. So we have then the intersection of the red-orange curved surface, the z function graph, with the plane, y equals y0. That's a key thing. That intersection is this black arc. That's the intersection of the graph of the function z with the plane y equals y0. So that black arc is what? It's like a regular graph, 2D graph. At that point, x0, y0, z0, then we draw the tangent line to that point in the plane y equals y0. The slope of that line is the value of the partial derivative at that point, which is what I have over here. The partial derivative of f with respect to x. So x is the variable, y is a constant. At the point x0, y0 is the slope of that blue line, which is the tangent line to that intersection curve in the plane y equals y0. And so here's the picture and kind of the whole ball of wax for the other partial derivative. The partial derivative with respect to y at the point x0, y0, and what that means. So we have all these ingredients. The graph z of z equals f of x. Y is the reddish type surface. All these points plotted. the plane as, so now we're going to be doing the derivative with respect to y. So x equals x0 is a fixed plane. So we're looking at that sort of, I don't know what color that plane would be actually. Here, plane x equals x0. So we look at that surface intersected with that plane. And that intersection is the curve that's done in black in this diagram. And the tangent line, which is in blue, the tangent line through the point x0, y0, z0 to that curve within the plane x equals x0 has a slope. And that's the value of the partial derivative at the point x0, y0. So the partial derivative with respect to y is equal to the slope of the tangent line to the curve in that plane x equals x0, or in the y direction. You can see that's that tangent line is in a plane which is parallel to the y-axis. And similarly, just to back up here, the partial derivative with respect to x is the slope in the x direction at that point, because the plane y equals y0 in this diagram is parallel to the xz plane. So the line, the blue line, is in the x direction in the first, and the blue line is in the y direction in the second diagram. So here's an illustration of this with numbers, slope in the x direction and the y direction. I want to verify this first before we do anything else. We're being told here f sub x, so the partial derivative of f with respect to x at the point 1/2, 1 equals negative 1/2. Let's do that calculation here. That's good practice. So let's do f of x, y is equal to negative x squared over 2 minus y squared plus 25 over 8. That's the surface that's graphed here. Okay. Now, to take the partial derivative with respect to x, allow me to write the first term as negative 1/2 times x squared. And then f sub x, which means x is going to be the variable now, and y is a constant in this derivative. So the first term is a regular old x derivative, negative 1/2 times 2x to the first. The second term is now a constant, so that differentiates to 0, just like the third term. So f(x), the partial with respect to x, of x comma y, is equal to negative 1/2 times 2 is negative 1x, negative x. Now what we're given up here, is it true? f(x), so the partial with respect to x at the point x is 1/2, y is 1. It's a point on the surface right here. That's equal to, so this is the formula for f(x) of x comma y. Now the formula doesn't depend on the value of y, only x. That's okay, that can happen. It can even be a constant, it can be equal to a constant. But in this case, the partial derivative only depends on x. So this would be negative 1/2, which is what we have here. Okay. Now, in terms of what that partial derivative being negative 1/2 means, geometrically, here it is. So the partial derivative of f with respect to x at the point 1/2, 1 is equal to negative 1/2. Means the slope of the blue line in the diagram in the plane y equals 1 is negative 1/2. And in this diagram, what's what? We have the surface, which is kind of this bluish color. We have the plane, which is sort of this off yellowish color plane, y equals 1. The intersection of that surface with that plane, within that the intersection of that surface with that plane is this black curve on which our point of interest lies. The tangent line to that curve has a slope of negative 1/2. So you have to put your 3D thinking cap on here and think about what that means. Is that if we're at this point, a slope of negative 1/2 would be going down 1 and over 2 like that. So that's the negative 1/2 in this picture, the slope of this line in the x direction. Now for the same function here, let's verify this. The partial derivative with respect to y at the same point, x comma y 1/2 comma 1 is equal to negative 2. And that's what's illustrated in this picture. First, let's do the partial derivative. Partial derivative with respect to y of x comma y means now differentiating with respect to y means x is treated as a constant. So the first term, negative x squared over 2, is a constant. The second term's derivative will be negative 2y, because y is the variable now, and the third term is a constant, so the derivative of that is 0. So in this case, the partial derivative with respect to y of x comma y is negative 2y. So now I want to plug the point in, the x comma y point, which is 1/2 comma 1. So the partial derivative with respect to y at the point 1/2 comma 1 is equal to, so now we're plugging in numbers. This is the value of x at this point, but there's no x in the formula, but that's okay. We plug in y, so negative 2 times 1, or negative 2. So that's where this comes from right here. Notice our surface is in 3 dimensions. Our input space is x comma y, the 2D plane down here. So the point 1/2 comma 1 is in the xy plane, 1/2 the x1. And then the z value tells you the height. That's the point that's plotted in 3D, x comma y comma z, 1/2 comma 1 comma 2. Now back to the partial derivative. So once again, we have this surface, kind of in the bluish color, 3D surface, which is graphed here, z equals f of x, y. We have a plane, which in this case is the plane x equals 1/2. And the intersection of that plane with the surface is that black curve, the arc. And at this point of interest, that black arc, that intersection arc, if you will, has a tangent line, which has a slope, which is negative 2. So fy, the partial derivative with respect to y, evaluated at 1/2 comma 1 equals negative 2, means that is the slope of the blue line in the plane x equals 1/2, the slope in the y direction. So where negative 2 is in the diagram is you got to start at the point in question, go down 2 over 1. That's the negative 2. slope.